Hello everyone, this is Bharti from Aeronautical Engineering. So here the course being called Aerodynamics. So from this course we have the tech talk called, the topic name is called Vortex Model of the Control of Flow. Introduction to Vortex Model in Aerospace. In aerospace engineering, the Vortex Model is a portal for understanding and controlling the behavior of fluid flow, particularly in the convent of aircraft aerodynamics. A vortex is the swirling motion of fluids, and this model helps predict the effect of a vortex structure on lift, drag, and stability of flying vehicle. Vortex dynamics also plays a significant role in the vehicle turbulence propeller design and control process. By applying vortex models, engineers can optimize aircraft design, enhance flight performance, and ensure safety, particularly in turbulent conditions. These models are essential tool for controlling airflow and improving aerodynamic efficiency. So, understanding the vortex flow concept. Vortex flow refers to the rotational motions of the fluid, often characterized by circulation of fluid around a central axis in aerodynamics. Vortex structure arises around wings, control surface, and engine exhaust. A well-known example is the vortex created at the wing tip, which is essential in understanding lift generation and include drag vortex models. Mathematically describe these swirling fluid patterns, providing a framework for engineers to analyze and predict their influence on flight dynamics. Vortex flow behavior is integral to the design and optimize an aircraft for both efficiency. The role of vortex strength in flow control. Vortex strength is a key parameter in vortex model as it determines the intensity of a rotational flow and its impact on nearby aerodynamic surface. The strength of a vortex influences the resulting lift, drag, and the induced airflow around an aircraft. For instance, and vortex strength at the wingtip affect the downward flow of air, contributing to the generation of lift, but also introducing drag in vortex control model. Understanding how vortex strength varies with flight conditions is essential for optimizing performance. Engineers manipulate vortex strength to achieve desired aerodynamic outcomes such as improved lift to drag ratios. Vortex lattice method in aerodynamics. The vortex lattice method is a computational technique widely used to analyze and model the airflow over aircraft wings and control surface. VLM divides the surface of the wing into discrete panels, with each panel represented by a vortex filament. By circulating the influence of each vortex on the other, and method provides a way to determine the distribution to lift and aerodynamic forces acting on an aircraft. The VLM is especially useful for analyzing subsonic flow and optimizing wing shapes, making a critical tool to design the phase of aircraft development. Introduction, drag and vortex interaction. Induced drag by a byproduct of vortex formation around an aircraft, particularly at a wingtip. When airflow over an aircraft wing is generated, a vortex leads to downwash and alters and the surrounding airflow. The disturbance creates additional drag that reduces the overall aerodynamic efficiency of the aircraft. Vortex model helps engineers understand the interaction between vortices produced by the aircraft wings and other edge surfaces. By studying this interaction, designs can devise strategies to mitigate induced drag, such as wingtips device. Example, winglets. The reduced vortex strength and improved fuel efficiency. Vortex-induced oscillations and stability. Vortex-induced oscillation occurs when the vortices generated by the airflow interact with the aircraft structures, components, causing vibrations or oscillations. These oscillations can adversely affect an aircraft stability, leading to potential control issues or even structural damage. Vortex model play a crucial role in prediction and controlling these oscillations by simulating vortex behavior and identifying the frequencies at which vortex-induced vibrations are most likely to occur. This models engineers can modify the design of an aircraft to induce or reduce oscillations, ensuring smoother flight characteristics and enhanced safety. Vortex wake and its effect on other aircraft. Vortex wake is the turbulent flow left behind the aircraft. It's a move around through the air that waves consist of series of vortices. Can be vorticity, it means the rotation over 360 degrees. This can pose significant hazards and to other aircraft flying in close proximity, especially in busy airspace. The strength and size of vortex wakes depends on factors like aircraft weight, speed, and wing design. Vortex models are essential for understanding the spread and disruption of vortex wake in the atmosphere, allowing for this development of the safe flight separation produces and wake turbulence mitigation strategies to protect following aircraft from potential dangerous conditions. Vortex control for aircraft lift enhancement. Uh, Vortex control is an advanced concept used to manipulate the vortex generated by an aircraft to enhance lift production by influencing the strength, position, and the direction of vortices. Engineers can optimize the lift-to-drag ratio and improve overall aerodynamic performance. Vortex control can be achieved through the use of various devices such as vortex generators, which induce small-scale vortices on the surface of the wing to delay load separation and reduce drag. Vortex control techniques are often employed in aircraft designs to minimize lift, especially in critical flight remains like takeoff and landing. Vortex generators for flow attachment. Vortex generators are small aerodynamic devices placed on the surface of an aircraft wing to manipulate the airflow. These generators create controlled vortices that helps maintain flow attachment to the wing surface at higher angles of attack or in the region of flow separation. By re-energizing the boundary layer and preventing early flow separation, vortex generator can improve the overall aerodynamic performance of an aircraft. In vortex modeling, these generators are incorporated to predict the effect on airflow and to optimize their design for maximum lift and reduce drag, making them a key component in advanced flow control strategies. Unsteady vortex model in turbulent flow. Unsteady vortex models are used to simulate the dynamic behavior of vortices in turbulent flow. This model takes into account the time-dependent nature of vortex formation and decay, which are particularly important in high-speed flow or during maneuvers in unsteady conditions. Vortices can change rapidly in strength, location, and structure, affecting the aircraft performance by simulating unsteady vortex behavior. Engineers can predict how turbulent wake and vortex interaction impact stability and control, allowing for more accurate flight simulation and better control over aircraft dynamic in challenging flow environment. Vortex interaction with aircraft control surface. Aircraft control surface such as ailerons, elevators, and radars interact with the vortices generated by the airflow around the aircraft. This interaction can affect the effectiveness of the control surface, particularly at high angle of attack or in turbulent flow conditions. Vortex models are used to study how vortices influence the aerodynamic flow on control surface and how they can be manipulated for better performances. For example, vortices created by the wing can alter the pressure distribution over the ailerons, affecting roll control. Understanding this interaction allows for more precise control surface design and better overall aircraft maneuverability. So, vortex structure and high lift system. High lift systems are crucial for improving aircraft performances during takeoff and landing by increasing lift without significantly increasing drag. Vortex structures play an important role in the functions of this system. Devices such as slats and leading edge devices generated that help maintain flow attachment to the wing at low speed and high angles of attack. Vortex model allow engineers to predict the behavior of the vortices, ensuring that high lift devices are optimally designed to maximize lift while minimizing drag to flow separations. Numerical simulations of vortex dynamics. Numerical simulations are increasingly used for the model vortex dynamics in aerospace engineering. Computationally fluid dynamics tool enable the modeling of complex vortex interactions, allowing engineers to analyze how vortices form and evolve in different flight conditions. These simulations provide valuable insight into the impact of vortex formation on lift drag stability, enabling more accurate predictions of aircraft performances by utilizing high resolution CFD simulations. Aerospace engineers can optimize aircraft design to minimize vortex-induced drag, enhance stability, and improve overall aerodynamic efficiency. So, vortex behavior in supersonic and hypersonic flow. In supersonic and hypersonic flow, flight remains the behavior of vortices changes significantly compared to subsonic conditions. Shock waves interact with vortex structure, leading to altered vortex dynamics and potential increase in drag instability. Vortex model of supersonic and hypersonic flow take into account that affect the compressibility, shock-induced separation in high-speed flow characteristics. These models are crucially for design high-speed aircraft and space vehicles, where vortex behavior plays a significant role in heat transfer stability and aerodynamic forces. Understanding this vortex interaction is a key to optimizing design of high-speed performances. Vortex-induced lift and aircraft stability. Vortex-induced lift is a phenomenon where the vortices generated by the aircraft surfaces contribute to overall lift production, while vortex-induced lift is a source of aerodynamic efficiency. Okay, excessive vortex strength can lead to the instability, particularly in certain flight remains. Vortex model helps engineers balance the benefit of vortex-induced lift with the potential risk of instability, ensuring that lift is generated effectively without compressing the aircraft stability. Understanding the role of vortices in life generation is crucial for design aircraft that are both effective and stable during the vortex flight conditions. Advanced vortex control techniques. Advanced in a vortex control techniques have enabled significant improvements in aircraft performance. Techniques such as active flow control, where vortices are actively manipulated using sensors and actuators, are gaining attention in aerospace research. These methods allow for a real-time adjustment of vortex strength and position, optimizing lift, drag, and stability throughout the flight. Active vortex control systems are used in conjunction with the traditional design elements to reduce drag, improve flow efficiency, and enhance maneuverability. This advanced technique required sophisticated vortex models and accurate predicted the effect of aircraft performance and behavior. Vortex behavior and propulsion system. In addition of aerodynamic processes, vortex plays a crucial role in propulsion system, particularly in a wake flow generated by engineers and propellers. The vortices created by an engine exhaust or propeller blades influences the flow around the aircraft fuselage and wings. Vortex models are used to study the interaction between the vortices and the overall aerodynamic forces acting on the aircraft. This knowledge is important for optimizing propulsion system design, improving efficiency, and minimizing drag. Accurate vortex modeling also aids in the design of more effective engine understanding and control vortex behavior in the propulsion wake-up. Vortex model in aircraft design optimization. Vortex model are integral to optimize and of aircraft design by understanding how vortices affect the flow over a wing control surface. And the other part of aircraft engineers can make design assessment to improve aerodynamic performances, for instance, optimizing wing shape or employing devices like winglets can help reduce vortex-induced drag. Vortex models also assist in designing more stable aircraft by controlling vortex-induced oscillations and turbulence. Ultimately, those models allow engineers to refine designs for maximum efficiency, stability, and safety, leading to more advanced and cost aircraft. So, at last, the conclusion. Vortex models are essential tool in aerospace engineering for controlling and optimizing fluid flow around aircraft, from improving lift and reducing drag to ensure stability and minimizing vortex-induced vibration. These models are indispensable in aircraft design and performance analysis. Through the application of vortex model, engineers can enhance the aerodynamic efficiency, maneuverability, and safety of modern aircraft. As aerospace technology continues to involve advancement in vortex modeling and control will remain crucial in shaping the further of aviation, leading to more sustainable and efficient flight technology. Thank you.